Hello, and welcome to the next episode of the AstroPhot tutorial series. My name is Connor Stone, and today we're going to be going through the Model Zoo. It's the tutorial that gives you a quick view of all of the different types of models that are available in AstroPhot so that you can visually compare them and see what's appropriate for your situation. As always, we have to start by importing AstroPhot and a few other libraries that we're going to need. We'll also just create a basic target. This is a dummy target, but we'll be using it so that all of the models are projected into about the same space. So it's just 100 by 100 pixels with a pixel scale of 1. Um, and that will let us visualize all of the different models on a comparable scale. To begin with, there's the sky models. These are the simplest set of models, and they mostly represent something that should cover the whole image or the whole fitting area that you're interested in. The simplest of those is the flat sky model. It's just a single number, this I naught value that goes up or down, and it goes up or down in all of the pixels. So that flat sky model is not especially interesting to look at. It's just a single value for all the pixels. But most images have some constant baseline in them, and so this lets you represent that. The next step up is a plane sky model. So it has that constant level, but then it's tilted in some axis. And that tilt lets you handle, say, a small galaxy that's next to a larger galaxy, and that larger galaxy's light is trailing into the big galaxy. Well, this is a simple way that you can account for that without needing to model the whole image in the very large object. You can just model the local region around the object you're interested in. That can be quite useful for that. The bilinear sky model is where the complexity starts to grow. So here it's just a grid of nodes that have bilinear interpolation in them. And so AstroPhot will interpolate between, in this case, a 5 by 5 grid of points, and that produces the smooth sky background. I've just taken random uniform values, so it looks kind of blocky in the actual model that you see. But if you actually fit this to data, it would probably be a more smoothly varying model. But it lets you essentially cancel out anything over a certain size scale on your image, which could be useful if you have, say, something a little more complicated than a nearby galaxy, maybe nearby large galaxy, maybe some cirrus or uh, two nearby large galaxies, which give you more than just like a smooth surface across the area you're interested in. Bilinear sky will let you handle that. Okay, the next thing to look at, aside from sky models, is your point spread function or your point source function models. So these models don't actually themselves go into your image. They represent the distortion in your image that's going to blur things. So, the simplest way to represent a point spread function is just with a PSF image. This is a static image that you've gotten through some other source. It could have been through like PSFX or PIF or something like that, that has determined what your PSF function looks like as a grid of pixels. You can just put that in here. And this PSF image, let's just show this one I just made up with some quick calls to a few functions. And this mock empirical PSF function, you could then provide to a given model, and that model will get convolved by this anytime that it gets sampled into the image. But we can do more than that. One is, what if we wanted those pixels to actually be something that we were going to fit? What if we wanted to fit the PSF model? Well, you can create a pixelated PSF model, which is essentially the same as the uh, empirical PSF model, except instead of being a static set of pixels, the pixels are now part of the model, and those make up the model. So you could do some optimization on your PSF at the level of individual pixels. This gets to be a really big fitting problem really fast, but it is available for you if you're interested in it. Another possibility is that you use it to add some perturbation to a simpler PSF model that we'll look at later. So here is the Gaussian PSF. This is a pretty widely used standard first go at a PSF model. It's not necessarily the best choice in any individual scenario, but it's so easy, people take advantage of it. It's just a Gaussian blob, and that would represent your PSF. MOFAT is fairly commonly used for ground-based observatories, but I'll stop here with all the different model types for PSF models and just note that you can have a Sirsic, Farrer, exponential, MOFAT, King, spline, Gaussian, or Nucher. You can have all of these different PSF models, and their appropriate parameters would be added to your fitting problem. So you can actually fit the PSF. We'll get into that in a future tutorial. You can add an ellipse version. So here we have, instead of a MOFAT PSF model, MOFAT ellipse PSF model, and now it's elongated along a certain axis. This happens fairly commonly, especially in the edges of an image where some of the optical distortions get more intense. The area disk PSF is sort of the idealized PSF for a circular aperture, which of course most telescopes have a circular aperture, but then they have more than just that. And so the area PSF isn't necessarily the best for any scenario, but it's right there if you want to use it. Um, Basis PSF is a really good sort of halfway point between the complexity of a pixelated model and the simplicity of a parametric model. So the basis PSF takes a basis set of models and just uses a weight factor on each one of those basis elements in order to create the PSF model. The simplest way to do this, AstroPhot lets you just say Zernike 4, and it will generate the Zernike polynomials for you as the basis set. Alternatively, you can provide essentially a cube of images here as the basis, and AstroPhot will use that cube. But this is the cube that AstroPhot automatically generated when you asked for Zernike 4. And so it gives you all of these different perturbation models, and then you multiply all of these by a set of weights, and you get a final PSF model out in the end. Okay, so we've got a PSF model. This represents the distortion in our image, but how do we actually get that into an image to represent something like a star or a supernova? That's with the point source model. So this point model right here essentially represents a delta function in our image. It has a position and it has a flux, but the actual shape of the model is entirely determined by its PSF. In this case, we're just using that basic empirical PSF target that we added. And now, because I've multiplied it by a flux, given it a position, this is actually in a modeled image now rather than just represented as an abstract point spread function. And because it's projected into a model image with a set of pixels, it's not going to look the same as the empirical PSF model because its light has been integrated into those pixels. And so there might be some overlap of neighboring pixels that projects into that image. This is now an example where I've used a different point model, but now you see its center and its flux is applied to a PSF model, a MOFAT PSF model. So this essentially represents a MOFAT point source in an image, and it would let you fit the center, the flux, and the MOFAT parameters of that PSF model. Okay, so we've talked about sky, we've talked about point sources. Let's get into extended objects, which for simplicity in AstroPhot we just call galaxy models. And there's a whole lot of extended model objects, galaxy models. This is a spline galaxy model. So it's elliptical isophotes. It's forced into an ellipse shape. But as a function along the semi-major axis, we've got just a spline function. It can be an arbitrary function of the semi-major axis to generate the isophotes of this spline galaxy. Very general, very flexible, but depending on your scenario, it might have too much flexibility and could get, especially in the center, a little wonky. So a little more constrained. The Sirsic galaxy model is the classic model used for galaxies. It's essentially a generalization of a Gaussian, So if your Sersic index, if it's zero point 0.5, that's a Gaussian. If it's 1, that's an exponential. And if it's 4, then that's a de profile. And all of those are sort of encoded smoothly between each other in the Sersic galaxy. If you want to restrict yourself to an exponential galaxy, you could force the Sersic to have n equals 1, or just use the exponential galaxy model, and it's a little more numerically efficient. Similarly, you could force the Sersic to have n equals zero point 0.5, or just use a Gaussian galaxy model. It's a little more numerically efficient. Now here's the Nuker model. This lets us generalize a little bit. It has essentially two slopes, one for the inner parts, one for the outer parts, and having that flexibility lets it handle uh, cases that necessarily the Sersic wouldn't necessarily be able to handle. It has a few more parameters, of course, in order to handle that, but the Nuker is a pretty widely used model. The Ferrer and the King models are useful because they have essentially a tail off, an end point of the galaxy. Or if they're used as a component, say the bar of the galaxy, these could be used to represent some component of a larger galaxy. And you can stack up components together using a group model from the previous episode, and uh, you would get you would get a more complicated and detailed model of your galaxy. So those are the standard galaxy models, the standard extended object models. And for each of those, there's a whole bunch of different variations, and we'll get into a bit of that. But there are some special galaxy models that have their own uh, detailed representation. So an edge-on model, this is specifically intended for representing edge-on galaxies. And so um, it has some properties that make it useful for that, such as the fact that it's isothermal along a certain axis. The multi-Gaussian expansion is essentially just a sum of a whole bunch of Gaussians. So here you can see the axis ratio. I provide a vector of values, and so that means that each of the four Gaussians is going to have a different axis ratio. I provide a vector of four sigma values, so each of the four Gaussians is going to have a different width. And AstroPhot just in a numerically efficient way combines those four Gaussian models into a single model. What's nice about the multi-Gaussian expansion is that it's easy to switch between a 3D uh, representation and a 2D projection. So at least under certain circumstances, you can deproject this model from the 2D sky into a 3D model. Uh, just beware that it's not always a unique deprojection. You can see the original paper for more details. A Gaussian ellipsoid is actually a 3D Gaussian model. The model itself is represented in 3 dimensions, and then we do the projection as part of the analysis of the model parameters to create the image that you see. And so what's neat about that is that you can do animations like this where I took a model and all I'm doing is changing the inclination of it, and you can see how it changes tilt, which is kind of fun. Another option, just like with the pixelated PSF model, you can make a pixelated extended source model. So here I've just added a uniform grid of pixel values, but you could in principle allow these pixels to follow any sort of representation. Alternatively, you fix the pixels to some known shape, and you can fit a center, a rotation, and a scaling. So that's another option for what you can do with the pixelated model, just depending on which parameters you fix or allow free. The basis model, like the basis PSF model, you just take a basis, a series of images, and the actual model parameters are the weights that multiply those basis elements, and then stacked together to make one model that you see. This is very general because you can use, like, say, an eigenbasis from a bunch of images that you've collected, and now you can your weights are weights in that, or a position in that eigenbasis that should hopefully cover the region of interest for the models that you're trying to represent. Okay, now all of the basic models, the basic extended object models that I mentioned before, the Sersic, Exponential, Gaussian, Moffat, Spline, Ferrer, King, and Nuker, all of those have some standard extensions to them. One of them is a superellipse extension. So you see perhaps faintly that there's a bit of an X here. That's actually just the way that it's plotted. What's happening here is the isophotes have gone from being a perfect ellipse to now a superellipse. In this case, they're kind of boxy. You can also make them disky, and this is quite useful for representing different kinds of galaxies, especially elliptical galaxies, but it's a generalization that gives you more freedom for the models just in general. The Fourier ellipse essentially allows you to take your ellipse model and add perturbations using Fourier modes. So you can imagine just tracing around the ellipse and bumping some parts out or pulling some parts in based off of a sinusoid. So the order of the sinusoid that you use determines what the where the perturbations are going to happen. And if you use multiple modes, say modes 2, 3, and 4, you can get relatively complicated structure for your final model. The warp model essentially makes it so that the position angle and the axis ratio of your model is now a function of semi-major axis, or at least what was originally the semi-major axis of your ellipse. It all gets kind of muddled together in the end, but you can use this to create spiral arms or other detailed structures like that that change as a function of radius as you go out in the model. So plotted here is what the model actually looks like on the sky. This is the Sersic profile because this is a Sersic warp. And this is the axis ratio and position angle as a function of radius, where this radius is the original semi-major axis radius. The ray model lets you essentially take two Sersic models but have one apply along the major axis and one apply along the semi-minor axis. You could go higher order in the ray, so you could have three or four or five rays, as many as you want, and they just let you divide up the angular uh, distribution of your galaxy model and then have different Sersic models along each of those, which of course can add a ton of parameters, but gives you a little more freedom sometimes when you want to just take a step past a pure Sersic, but you don't want to go to, say, like a pixelated model, which just has an absolutely gigantic number of parameters. A wedge model is just like the ray model, except instead of smoothly varying between them, it just has a harsh cut and it jumps between the two different models, depending on what's more appropriate for your image. Okay, so those are the core models in AstroPhot. You can make your own models. We'll get into that in a future tutorial. But there's one extra thing that I've put in the Model Zoo tutorial because it seems like the most appropriate place for it. And that is the idea of a batch model. So you can take any model from above, in this case, the Sersic Galaxy model, our classic test model, and this Sersic Galaxy, we're going to put it into a batch model, kind of like how you create a group model. This is a batch model. And the batch model essentially now lets you take the original parameters from this model, and instead of providing a single value for them, so the center has this vector of length 2, the axis ratio is a single number. Now we're going to provide a vector of values. So for the center, we're going to provide 5 coordinates. For the axis ratio, we're going to provide 5 axis ratio values. And for the position angle, we're going to provide 5 different position angles. And this batch model will vectorize this initial model that we created and just create them all, add them together, and put them into the same scene. So here we've got 5 Sersic models that we created in a really numerically efficient way, but from one actual like Sersic AstroPhot Sersic model that we created, and then just batching over that, which is very powerful. There's also a batch scene model, which essentially lets you do this same vectorization element, except across multiple images. We haven't gotten into joint modeling over multiple images yet, but that's the main idea of what this batch scene model lets you do. And you see, you can make it so that the parameters change across different images, or not, depending on what's appropriate for you. But you can see this like little point source here. You can see it's getting dimmer across the images. And that's because we're allowing the parameter for the flux to vary across multiple images, which is super useful for time domain analysis or multi-band analysis. Okay, that's actually the end of the Model Zoo tutorial. And I hope that you now feel ready to take an image that you're interested in and figure out which model would be appropriate to use that. You can scan through the model zoo and see which one matches up better, or take a model that you think is about right and add some perturbations to it and make sure that it represents your image as well as you need it to for your science. As always, contact me if you have any questions about these models, about their parameters. And with that, I think that's the end of the video. Thank you. Bye.